here's a solution to the last problem in section 9.1. Here we're actually trying to get a maximum error on the remainder regardless of what value of x somebody puts in. And so this is a little different than what we were doing before. But we use the same formula. And then rather than think about what is the maximum error at a particular point, we think what is the most that this error bound ever tells us over an entire interval of values. But the process is exactly the same. Here we see we're using a quadratic approximation, a second degree approximation for this log function. And so that means that the remainder according to our theory, is no more than, and of course that's just absolute value, but m times the center of this is 0, so I'm not going to put x minus 0 in here. I'm having a hard time going back and forth. So the theory says that the upper bound on the error for a second degree polynomial is based on x cubed over 3 factorial, where x is the number you're plugging in. And so here, that's not a specific number. It could be anything between minus 0.01 and 0.01. But this is still a legitimate thing to say. And m has to be an upper bound on the third derivative across all of these points. And so to do that, I'm going to have to know what the third derivative is. So I'll do that over here. We know the first derivative, this is 1 over 1 plus x. That's the log function's derivative. Second derivative is, so that's 1 plus x to the minus 1, so it'll be minus 1 over 1 plus x squared. And I'm running out of room. Third derivative, third, is that 3? Okay. Third derivative, again, this one before it is really minus 1 plus x to the minus 2, and so one more derivative will give me a 2 on top and a 1 plus x cubed on the bottom. So that's my third derivative is 2 over 1 plus x cubed. So to figure out what the m is, now notice this is multiple choice, so I don't have to read the graph very carefully. They just give me a bunch of whole number values, so they're not asking me to read the graph very, very closely. But I would still want to be able to look at a graph and get a better estimate. So I'm going to pop open here, let me pause this, and pop open a picture of the third derivative. Okay, so I'm back. So down here on the left is my derivative. You can see that I just went to Mathematica and pulled it out. So I'm asking it to plot 2 over 1 plus x cubed. That's my third derivative. And I'm actually asking it to plot from minus 0.02 to 0.02. I know that's more than I want to see, but I want to get a feeling for the whole thing. So just this part is what I care about. And you can see the largest that this third derivative ever gets is over here, a little bit more than 2.05. So an m value of 2 is not big enough, but an m value of 3 is. So of the choices, if I were trying to get an estimate myself, I'd probably just use m equals 2.1. That's clearly big enough, and it's a nice number. So 2.1 is bigger than all the. Again, all I care about is what's between minus 0.1 and 0.1. So 2.1 would be the value of m I would use if I were doing it myself, but since this is multiple choice, I just have to use the first m that's big enough, and that's going to be m equals 3. So this is that's the only one of those options that will that'll work. It's the smallest m that they gave me that's bigger than all of the third derivative values. So back here, I'm saying this is less than, this is no more than x cubed over 3 factorial times this m, which is 3. And that's true regardless of what value of x you use, as long as you're between minus 0.01 and 0.01. And so to get the upper bound on the error that works for all these things, I just have to think about what is the very biggest this can be when x is between negative 0.01 and 0.01. And since it only involves the x cubed function, it's pretty clear that the biggest that will be is when the x is as big as it can be. So the largest that x can be is 0.01. And so putting the largest x you can into this formula will give you the largest value you can get here. If you're not sure about that, you could also plot this guy over negative 0.01 to 0.01 to see how big it gets. But I'm sure that this is as big as it can be when the x is as big as it can be. So this is no more than 3 times 0.01 cubed over 3 factorial. And again, don't be afraid to look at a graph if you would like to. This is the problem, is what's the biggest that can be. But because it's just a power of x, I feel pretty comfortable that the largest that a power of x can be is when the x is as large as possible. If you do the arithmetic here, you get, and again, they want it in scientific notation, so I get 0.00005. So I get, this is 5.0 times 10 to the minus 7 is what this evaluates to be. So this will be the answer that goes into that box when m equals 3. So the actual error at any particular approximation in here might be smaller than that, but that's the worst that the upper bound of the error, that's the largest the upper bound of the error can be for values of x between minus 0.01 and 0.01.